Okay, so let's take a look at this. If you are watching this from home, that's because you're absent today. This is our plan. This is the 18th of February, or April, sorry. We are looking at a lighting in series versus parallel, and then we're going to do some other things here. So hopefully, if you're gone, you can pay attention through this video. All right. Anyone willing to take a risk here to answer which of those configurations would produce more light, either the series or the parallel? Okay, no one is offering, so I'm going to ask them to raise their hands. Close your eyes. Close your eyes. You believe it is the series combination. That's letter A. The series produces more light. Okay? And then put your hands down. Raise your hand. You believe it's the parallel combination that produces more light. Okay, we have, raise your hand if you have no idea. And there's a few people. All right, so thank you. We had a few say series, more say parallel, and then a few people said no. Let's go ahead and analyze this then. Would you guys agree that the brightness is based on the power being delivered? Would you guys agree with that? Okay, so let's do some equations over here. Power is equal to I times V. Power is equal to V squared over R, where power is equal to I squared times R. So if I want to determine which ones are brighter, I might be able to go through and look at it from a power standpoint. Now, they said that the equivalent resistance, that the filaments all have the same R values. So any place that I see an R, that should be the same for any one of those things. Would you agree with this statement, that the current flowing through the series light bulb, the current flowing through there is less than the current flowing through this light bulb? Would you agree or disagree with that statement? The current flowing through the series is less than that throwing through that individual light bulb in the parallel. Agree? Okay, you should agree with that statement. And the reason for that is that the resistance here, would you agree that resistance here is 2R? Since those things are in series, that the resistance there would be 2R? Would you agree that the resistance of this one is just R? So if I want to find the current flowing through this, I would be equal to delta V over their equivalent resistance. I would have half the current flowing through that one than through this one. So that I would be twice as great as that I. Now, you also have a difference in voltage. Let's take a look at that one. Do you notice that this one here, if this is a 12-volt battery, that this one would get 6 volts and that would get 6 volts? Would you agree with that statement? Each of those would get half the voltage, whereas this one gets an entire 12 volts and this one gets an entire 12 volts. Not only is there more current flowing through each of the light bulbs in the parallel resistance, they actually get twice the voltage that's being applied. There is much more light being generated here. So these will give off a lot of light. These things here, very little light. Which way is your light bulb? Which way is your car wired? If this is coming from a 12-volt battery in your car, which way is your car battery wired, or your lights wired? Parallel or series? How do you know? When one burns out, you don't want them both going out. So when one burns out, the other one's still able to operate. Okay? So we can use our power equations to be able to look at this. We could look at just in terms of voltage and so forth. We'd be able to get through and do that. All right, let's go ahead and take a look at this now. This represents what's called a combination circuit. You notice when I look at this picture off to the right, I have a light bulb C that is in series with 2 light bulbs that are connected in parallel together. So this arrangement of light bulbs is showing what's called a combination circuit. I have a series, letter C, so letter C is in series with A and B, which are in parallel with each other. So some concept-based questions, just to see if you can figure this out before we start showing you how to analyze a circuit like so. When switch S is closed, so right now S is in the closed position, how would the brightnesses of A and B compare to the brightness of C? Take a moment, talk that over with people at your table, see if you can reason through how their brightnesses would compare. So take a moment, A and B compared with C. Turn it on.
A and B would be the same, and C would be greater. Because yeah, the C would obviously be greater, but what does he have? It would be half.
Okay, I'm hearing some good discussions. Unlike the other one, where no one was talking, people are talking in this, and that's good. Would you mind sharing? And you're right on track. Would you mind sharing what you thought there, Kevin? You're on track. You got the right
A
idea.
and B are going to be less than C.
Okay.
So.
A and B will be less than C. You also said something about their brightnesses being the same. That A and B would have the same brightness? They're in parallel with each other. Shouldn't they have the same voltage drop across them because they're in parallel with each other? So whatever the delta V is across A, it should have the same delta V across B.
Yep.
Right. If I took a VOM meter and connected, those are at the same height, if you will, on the track. And so they have the same delta V. They're the same resistance, so they should have the same light bulb, the same brightness. Good. Now, why are you saying C is brighter? You're correct, but why are you saying, what reasoning could you use to say that C is brighter than A and B? What would be the reasoning?
Because the voltage from the battery goes to C first, so then when it's going to A and B, it'll drop down. It splits into A and B.
Okay, did you guys catch that? And thank you for trying it. Thank you for trying it. Because C comes from the battery first, it's going to get that voltage before it goes through the other ones. So would you say then, if I change this arrangement, I want to see if you would agree or disagree with this, and I bet you some people might look at that and say yes or no, I'm not sure. What if we changed it to be like this, and I had C afterwards? Would your answer to that question change? If I had this be A and then B and then I had C there, would the order of that light bulb in that circuit affect its brightness? Do you think it would? Yes or no?
Yes.
Okay, there are people that are saying yes. It's tricky to analyze that. You're going to find out that as we go through that, the order of that doesn't matter. It does not matter. You'll see that can be a challenging thing to be able to fully understand. But it doesn't matter that C comes first. And as we go through and we learn more and more about analyzing these circuits, you should see that it doesn't matter. Okay, go ahead. What do you think? It is correct that C is going to be brighter, but we're looking for some reasoning for that, regardless of where it's located. What's your thought there? It is brighter.
Due to the resistance of C being the same as A and B, only a certain amount of electricity can flow through C, which would mean you can't draw more current through something without changing the voltage or changing the resistance.
Okay. I mean, you're trying. I appreciate it. I mean, I do. I appreciate it. I'm glad that you guys are offering some explanations here. We're still a little bit new in our understanding of electricity, so you might be using these terms incorrectly. We're gonna try to get through this. Go ahead.
Does that have to do with current?
Go ahead. Say it one more time. Listen close to this, because I think we're onto something. Go.
Does that have to do with current?
Okay, let's look at the current. Would you agree that there's a certain amount of current flowing through this one?
Yeah, that's
We haven't determined what that is yet, but we have a certain amount of current flowing through that. What has to happen, if I think of power is equal to I squared times R. Now, all of these have the same resistance value, correct?
yeah.
Okay. What happens to that current when it gets to this point? What happens to it? It's got to split.
Yeah.
What that means is that some of that current is going to flow this way, and some of that current is going to flow this way. Now, if these are equal, would you agree that this would be I over 2 and this would be I over 2? Would you agree that they have to split? What does this tell us about the amount of power being delivered to this one compared to the amount of power being delivered to those? How many more times power? How much more power do I get as a factor?
No, quarter.
I squared times R, correct? But I'm squaring that I, and when I square I over 2, don't I get I over 4? I squared over 4?
Oh yeah.
So this would actually be 4 times brighter. I would have 4 times the power going through that one. If this is a certain amount of power, that's a certain amount of power, that one would be 4 times brighter. And how do I know? Because it's getting twice the current. When I get twice the current, I get 4 times the amount of power being delivered from that I squared times R. Now go ahead, say it one more time.
What happens here? We have 3 of them.
What if I had 3 light bulbs in here instead of, so add another one like so?
We just divide by 3 and it'd be 9.
Let's analyze it for a second. Let's make it be something like that. Clearly, D is going to be a lot brighter than AB. AB and C would all be the same brightness because they all have the same delta V. They all have the same resistance. I could go V squared over R and say, yeah, they have the exact same power. But now, this current, would you agree that the amount of current flowing through here, it doesn't matter that it comes first or second, it doesn't matter. But if this is I, all of that current flows through D. But 1/3 of that current flows through here. Would you agree with that? That the current has to be subdivided into 3 paths now?
Yeah.
What's 1/3 squared?
9.
A 9. That would make this one 9 times brighter than those things individually because it's getting 9 times power. Do you guys see how that?
Yeah.
Okay, that's what we talk about when I have a series in combination with a parallel. Okay, so we're going to try to analyze that. And we'll continue to go through much more complex circuits than just this. But this is showing you how you might apply some of those principles. Go ahead, Kevin.
So, but like when it goes through one light bulb
Yep.
to another, doesn't the amps drop? Like,
What do you mean by the amps drop?
like when you have your normal circuit, like the amperes, like because they add up to the total.
Mm-hmm.
So
If I put some numbers here, if I said this was 2, if that was 2, then this would be 1, and this would be 1. Right? So 2 coming into that junction has to split into 1 and 1. Now in this case here, this would be 1, 1, and 1, and that would turn to 3. So here it's increasing, right, as the other one was decreasing. It really what's important is how much current is flowing through those light bulbs.
Well, when it goes
Go ahead.
from one light bulb to the other side of the light bulb, does that change the current at all, or is it equal?
Let's try this one. Do you guys hear that question? When it goes from one side of the light bulb to the other side of the light bulb, does that change the amount of current?
Yeah.
Would you agree that that filament, that one portion of that filament is in series with the preceding portion of that filament? That all the current that flows through this portion of the light bulb flows through that portion of the light bulb? Would you agree with that?
Yeah.
That filament, the later part of that filament is in series with the earlier part of that filament. In series, it shares the same current.
It just doesn't slow. It doesn't
Yeah.
slow down at all.
Nope. Do you guys remember when we were passing our tennis balls around? Passing the tennis balls around, we did that as a fun activity, but it should help you get a visual model of this. That the flow rate of tennis balls moving through this portion of the circuit matched the flow rate of the particles moving through that portion of the circuit. It had to,
Yeah.
right?
Yeah.
It had to. So no, I don't slow that current down at all. Good?
Yeah.
Okay, let's try this one. What happens when switch S is open? Now, I got a bunch of stuff there. I'm going to try to get rid of that. By the way, folks, if you're thinking about this and you're struggling, wonderful, because that's what I want. Is I want you to think through it and I want you to struggle. You should be struggling through it. None of this stuff should be like a walk in the park, because if you've never studied circuits and you don't understand how voltage, current, resistance, and stuff works, it's going to be confusing. So I'm glad that you're struggling a little bit. The struggle is good. Let's try this next one. What happens when switch S is open? So I'm going to take this one here. It was closed, and I'm going to open it. What happens? Open-ended, turn and talk. Just, yeah, turn and talk. What do you think happens?
and will be off, and then B would get brighter, right? Because the flow,
Yeah, you guys talking. Just
the
talk.
flow of the electrons isn't cut in half anymore.
Is the like C would be equal series, so you could just because there's a draw.
Oh, it would be wait.
So the voltage would draw. Which would make the brightness less than C, but it's greater than S before.
What do you think would happen? Would you be willing to try it? Look at folks. If you're sitting there going, "Oh my gosh, everyone else gets it and I don't," you're wrong. Everyone struggles through this. So what I'm looking for is people just to provide some thought process. And it's okay. We respect you if you get something wrong. Go ahead.
It'd be a series circuit instead of
C and B would then just be in series.
yeah,
So what would happen?
same brightness.
These would be equally as bright as each other because that's gone. What would happen to the brightness of C compared to the previous trial? What would happen? It would decrease. And the reason for that is that essentially what I've done is I've increased the resistance of that circuit by disconnecting that path. I provide more restriction. Because instead of me having a small value of resistance here, I increase the resistance of that one to match that. It's going to lessen that current. These would be equally as bright as each other, but the overall letter of C would dim from what it was before. Go ahead.
Wait, how would B lower C's brightness if the electrons are going through C first?
Let's check it. I'm so glad that you guys are asking us. I'm really glad to see that you guys are thinking about this. So we're going to draw this circuit really quickly so you can see it, right? So we don't often have a chance. So let me do this FET circuit lab. And I can build this really quickly. I've done these things before, and so I'm just going to build that circuit really quickly. And I'm really glad that you guys are asking. So give me a second. So let's try this. We have a battery here. Doesn't matter where that battery is, but I'm going to put it down on the bottom. We're going to build something that looks just like this. So just give me a few minutes. Not even a few minutes, more like 30 seconds. We had a light bulb up here, correct? And then we had another path over here where we went down to one light bulb. Did we have a switch in the upper portion? Is that right?
Yeah.
Okay, so we're gonna build this really quickly so that you can sort of see how this happens, right? It's one thing to talk about it; it's another thing to actually see it. So let's go ahead and do this. And I'm hoping that I've done this correctly. I'm going from memory here. This look right?
Yeah.
And then we have one more connecting line from here to there. I'm drawing it exactly the way that we have it there. Let's first just check and see what happens. Let's zoom out just a little bit. Can you tell by looking at that that's brighter than those? Okay. Now I wish I would have drawn that in a different spot so you could see that one up there. I don't think I can change that at all. But watch the brightness now. Just watch what happens. First of all, the current. Let's try this for a second. Let's throw a current. Let's throw a current meter in here for a second so we can see this overall. So I had you guys do this stuff before, right? Just as a quick little thing here. There's a measure of our current. I have everything operating at 0.6 amperes flowing through that portion. Would you agree all of that 0.6 is flowing through that one? Would you agree that this one has to have 0.3 flowing through it? Now it's 0.3. Would you agree with those things? Okay, that has to be the case. Kirchhoff's current law says all the current coming into that node has to equal all the current going out. That's one of those things. Wonderful. All right, now, when I open up the switch, watch what happens to the current. You guys notice that that current went from 0.6 to 0.45? What I've done is I've taken this portion and I've made it more restrictive. And how I did that was by closing off that path. If I don't allow charges to flow through that light bulb, this portion of it, right, that circuit went from R over 2 to R. Would you agree the equivalent resistance of this is R over 2? If that's R and that's R, when I put them in parallel, it becomes R over 2. It has those. Now what I've done is I've made the equivalent resistance of this just R. Effectively, what that did is that increased the amount of resistance of this entire circuit. And sure enough, that current went down. That got dimmer. As Colton predicted, that brightness is the same as that brightness because it's now just a series circuit. But that right there changes the equivalent resistance of that circuit. Did the visual help a little bit to see how that happened?
Could you
Go ahead.
reverse it so that the electrons are going to the C light bulb first? Like the one on the
You just want to see whether or not it actually matters?
Yeah.
I absolutely can. I'm going to do it really quickly here. So just give me a minute. Remember that number is 0.6, right? So all I'm going to do is I'm going to delete that portion. I'm going to delete that portion. We're going to put that thing over here. And it's going to take just a moment.
Flip the battery.
Oh, I suppose. I suppose we could do that.
This guy's smart.
Take this thing and flip it.
Yeah.
Yeah, see, it says flip battery.
Where's it say flip battery?
Left.
Right there?
There you go. There, same thing.
I like doing things the hard way, so I would have moved that over here, and that's okay. But yeah, there you go. It doesn't matter where it is. Do you see it? Okay, good. All right, guys, I'm glad that you're struggling. I really am. That's an important thing. All right, let's take a look at this. Yeah, what happens if bulb C burns out? So just take a moment. It's an open-ended question. If bulb C burns out, what happens? Turn it on.
Does A and B just become the same thing, but it makes like a C circle?
Bulb C burns out. What happens?
The whole thing explodes.
Wait.
Bulb C, the filament burns.
Does that mean that it can't go through with the
Yeah, we're going to say it's an incandescent light bulb where the filament, the current flows through the filament, sort of like what Edison developed, right? Edison was not doing stuff with LEDs and stuff like that. That's what I'm saying. Would you guys agree what would happen with bulb C? Everything shuts down? If bulb C opens, there is no way, we don't have a complete path anymore. And so there's no way for charges to be able to flow through that circuit. So everything would shut down. Everything would shut down. I don't know if I can simulate that over here. I can't make this bulb burn up, but I can disconnect this line right there. So you notice if I disconnect that, then everything shuts down. Can I make it burn up? How do I do that?
Or the resistance off, or
I can't seem to make that thing burn up, but that's okay.
You could delete it.
Well, that's all I really did there. If that thing burned out, then everything shuts down. All right, one last question. What would happen to C's brightness if switch S stays closed but bulb A burns out? What would happen to C's brightness?
It would decrease a little bit because the A is making the resistance.
Would you agree that that's essentially the same thing as S opening? Yeah. So if A burns up and S is still closed, then essentially it's the same. It'd be the exact same thing as this right here. These two things are literally the same statement. Simply because that switch is allowing the current to flow through A. If A were to burn up, that's essentially the same as opening up that switch. Okay? All right, now, the challenge here, folks, oh, by the way, I was going to do this as a little demonstration. So I'm going to try this here. This is a visual. So I want you to see that in real life, this is also the way that it would work. It's not just on a simulation. So this little box was made up before me, and I'm going to use this as a visual so you guys can see it. And then I want to see if you can make a prediction as to how these things are actually wired. So let's go ahead and turn this on. Okay, so I'm going to hit this here as a, is the mouse on there? Do you have the mouse?
Yeah, I didn't know it was connected.
That's all right. Works easier if you guys could actually have this in front of you, but I have 9 bulbs. I'm going to go ahead and increase the brightness there. And so let's see. The 9 bulbs are labeled 1 through 9. And hopefully you can see upper left-hand side over here is 1, that's 2, that's 3, lock in place. Okay, lock. Now you should notice first, I have 3 different circuits here. 3 circuits. And so I have 3 light bulbs connected in some arrangement. And so the nice thing about this is I can just push down on one of these things here and remove it, and then you can see what happens to the other light bulbs. Can you see that when I take out 1, that 2 and 4 go out? Okay, take out 4, 1 and 2 go out. I take out 2, and 1 and 4 go. How are 1, 2, and 4 wired? How are they wired? In series. So there's a series connection between 1, 2, and 4. Now those are completely independent from these other ones. One thing you should probably notice is that 5, 7, 8, and 9 are all about the same brightness as 1, 2, and 3, but 6 and 3 are brighter. Propose something, Logan. Propose something. What do you want me to pull up? I did 1, 2, and 4. I know those are connected in series. Tell me something to do. What do you want me to do? Say which one? Pull out number 8. So let's pull out number 8 and see what happens. So I pull out number 8, and what I notice when I pull out number 8 is that 9 gets brighter and 3 gets dimmer.
Okay, so they're in a parallel.
Well, how are they wired? That's really the question. Now, you want me to pull out 8? I did. What else? Clearly, 8, 9, and 3 are connected together in some way. What do you want me to test next? We pulled out 8, and we noticed that that made 9 brighter. It made 3 dimmer.
Pull out 3.
Okay, let's pull out 3.
That'll tell you what one's in the circuit after.
I pulled out 3, and 8 and 9 shut off.
So they're in a parallel circuit. And that one's in front.
What if I pull out 9?
It's going to make 8 brighter and 3 dimmer.
How are 3, 8, and 9 wired?
8 and 9 are the parallel.
Which one is A? Which one is B? Which one is C?
C is the bright one.
C is the bright one. And so you can sort of see that. I want to go back to this for a second. Letter C, this one up here, all the current through A and 9 is flowing through letter C. So if I open that up, it shuts that one down. If I take out position A, that makes 9 and 3 equally bright, and you should notice that 3 actually gets a little bit dimmer from that. Okay, so a little connection from that. All right, let's try this one. Clearly 1, 2, and 4 are connected together, and it looks like those are connected together. And can you see that 5, 7, and 6 are connected? How are they connected?
Well, find out, aren't we? It looks like a parallel circuit.
Not completely parallel, and how I know it's not completely parallel is that these things will affect each other. Can you guys see that now number 6 is the bulb C in that circuit? And then these things here are A and B. Now, it doesn't matter whether or not 6 comes first or it comes at the end. All of the current flowing through those light bulbs, all the current flowing through here is flowing through that. And it doesn't matter whether or not it comes before or after, because the current's either going to split or it's going to combine. Okay? There you go. Now, we have a bunch of stuff that we have to do. This takes a while. Like, I'm not going to show you how to analyze this kind of circuit. I'm going to do that Monday, Tuesday, and stuff of next week. What I want to have you guys do is I want to have you guys spend some time doing what's called an equivalent circuit or equivalent resistance for circuits like this. So I have a little interactive. That interactive is posted out here for you. And when you open this thing up, when you open it, it's a document, and again, I refresh your memory that you are not to share these documents with other people, right? So this is an electronic digital copy. You should each get one. I'm going to show you this video here. And this video, I did record it, and for people that are gone today, you should watch this video. Watch that video. It's attached to that document. I'm going to stop the recording here because otherwise it's a recording of a recording. That's not very good. But watch that video if you need some help. I'm going to do that for everyone.